Hi, I'm Rich Hickey, and I'm the author of Clojure, and I'm quite thrilled and honored to have Clojure be part of Hopple. And sorry we can't all be together, but I appreciate you coming and watching this talk. It's a long paper and a long timeline, and I'm not going to go through it all linearly, but if you're not aware, Clojure was developed starting in 2005 in a self-funded sabbatical. And during that sabbatical, I didn't know I was going to write Clojure or anything else, but I was intent to do something that I found interesting and not care what anybody else thought about it. And that ended up becoming Clojure. But it's certainly the case that I wasn't trying to satisfy any external objectives, and so there's a lot of opinionated aspects to the design and implementation. So beware. Hopefully Clojure has pointed out some problems. I think some of these problems were things that I was aware of, and some of these things were undercurrents, if you would. But the dominant one was, in my opinion, programming had become too complex. I was a C++ programmer, then a Java and C# programmer, and what I frequently saw was projects, come up to speed, build out, get to a certain point, and then get crushed by their own complexity. And so, having done that for a little over a decade and a half, I was pretty tired of it. Had discovered Common Lisp and sort of fell in love with how different it was from what I had been doing, and how much simpler it was. And I said, that's what I want to do. I want to try to figure out a way that I could program in Lisp. But the other thing I fully expected was after my sabbatical, I would be going back to being a professional developer. So if I was going to make something, I'd have to make something that could be used at work, in consulting jobs and things like that. So to break these down a bit, programming complexity, I found in practice, was driven substantially by the fact that programs were imperative and that state management became something that was not manageable after a certain point. And even before you got into concurrency and some of the promises of multi-core at the time, people were just drowning in the update in place programming that was common using object-oriented languages. In addition, the languages themselves were just getting more and more complex, especially C++. It just had more features, and I was quite enthusiastic about them initially, but in practice, applying them with best practices, I didn't find that we had commensurate returns to the complexity, and people were no longer pointed at the complexity of the problems we were trying to solve, but pointed at the complexity of the tools we were trying to use. The other thing that was my experience was that using object orientation as was practiced at the time in those languages, so C++, Java, and C#, you ended up with a ton of concretions over time. Classes are the way you do everything, and you end up with a class for everything, including things like information, like customer classes and things like that. And in the end, what happens is every class is its own mini language, and all consuming code for that class is specific to it. And over time, you end up with hundreds or thousands of these classes and a very brittle application with code that's very dependent on your decisions about how to organize things and how to name things and what you put in each class. So if you're trying to make something to be, something you're going to use at work, the things I thought were cross-cutting that really mattered were that you can't actually just throw away your existing code base. That, I'm trying to imagine going in back to places where I was consulting or talk to my friends and say, here's a new thing, just stop doing what you're doing and do a new thing. People have big investment in what they're already doing and can't throw it away. Another thing that's quite important to professional developers is the access to libraries. In two respects. One is you don't want to write everything yourself. You don't have time to do it. People are already then were used to being able to find libraries for database access and I/O and graphics. And if libraries were specific to each language, any new language, you would be sitting there waiting for the language to re-implement the wheel or wheels. So that's also a challenge. The other thing I found, having moved from the traditional commercial object-oriented languages of C++ and Java and C# to Common Lisp, was there was this big emphasis on lists, but in my experience, linked lists in professional code bases were pretty rare. They were rarely used. Everybody uses vectors, arrays, and hash tables for performance reasons. And what I saw in Lisp and other functional languages was, the elegance and beauty of writing code with lists and recursively, but I knew that wouldn't be acceptable from a performance standpoint. So these were things I thought were concerns. Like I said, having pretty much not been aware of Common Lisp earlier in my career, moving to it and discovering it later was like an aha moment. I felt like I had been wasting my time becoming expert in C++. And I built a bunch of things, including things for customer engagements, where I prototyped or even built solutions in Common Lisp, only to have them say, "That's great, that looks really good, please rewrite it in C++, or Java or C#. And the trend certainly at the time was towards Java or C#. If someone was going to move away from C++, it would be to Java or C#. And the whole idea of a completely alien language with a different deployment strategy was just not acceptable. And then there was the whole lack of familiarity and kind of the knee-jerk response, which is well known, to Lisp's syntax and the parentheses and whatnot. The other thing I found in programming with Common Lisp is that it's not inherently a functional language, but there's plenty of functional algorithms and functional use of it. By convention, there are a number of things that are functional in the standard libraries. The functional things tend to have linear performance because they're built on top of the lists. So things like A-lists or associative lists are quite easy to use, but they have terrible, performance because they're linear. And the performant thing, so Common Lisp is a practical systems language that has vectors and arrays and hash tables, were not functional. They were imperative. So not only did you have to switch away from functional programming, but you really had to change your code. The interfaces were totally different. And so you couldn't write something small that you then turned into something large without really changing gears and rewriting. Other aspects of Common Lisp, as later I'll talk about wanting to pursue functional programming, was that the bottom of Lisps were con cells, which are mutable. In addition, the libraries that manipulated them manipulated that concrete data type, not via some sort of an interface or protocol. So that's not great, especially coming from object-oriented programming, where at least interfaces or virtual functions are quite common to give you some indirection between the abstraction and the representation. You'll see later, I'll talk about some of my attempts to bridge between Common Lisp and Java or C#, and they were not successful in the end. The things I didn't care about and still don't are being novel, inventing a new thing, solving some research problem or whatever. This is a tool building exercise designed to make a practical thing you could use for practical work, and I didn't really care and don't care if anything about it is new, and I do not claim any aspect of Clojure is novel. Another thing I don't care about and didn't was whether or not it was purely functional, trying to solve the problems of, can you do programming purely functionally, and how to do that, which some languages try to tackle. Even though I just mentioned it as being part of the objections to Common Lisp, having worked with Common Lisp, I was firmly in the camp of the parentheses and the code as data, and that notation is a feature. It's not a bug, and it's something you should deal with. And I wasn't going to try to accommodate people who wanted something more familiar. I was happy with it. I thought it was a feature. I still do. And so that's not a problem. Again, because Common Lisp and Scheme both had these issues at the bottom, I wasn't going to try to either embed in one of those languages or remain compatible with them. So that was not an issue. And I wasn't interested in any more of a type system, or even as much of a type system as Common Lisp had. I like the dynamic typing, and I knew that being hosted on one of these runtimes, I would get at least enough of a runtime type checking system that I wouldn't want to be inventing something on top of that. So again, Clojure is not new, and in fact, what was great is it's not really a from scratch language design. It's Lisp. It takes advantage of almost, at the time I started, 50 years of prior Lisp knowledge and tons of papers, and absolutely standing on the shoulders of people standing on the shoulders of other people. So there's that. The other things I did before 2005 were some experiments to try to get Common Lisp to work with these environments I knew I needed to have in production, the CLR or the JVM. I had written a little toy Lisp interpreter on the CLR, which was mostly about trying to interoperate, to write in Lisp but interoperate with libraries. Another project following that was something called JFly, in which I embedded the JVM inside Common Lisp using Farm Function Interface and JNI. And that was okay, although the JVM ended up sort of destabilizing the Common Lisp runtime, which was more oriented towards running for long-term in an interactive environment. I mean, JVM is great at running long-term, but the interaction and probably some bugs in the implementation made it less stable than Common Lisp on its own. And finally, in order to get a separation between the two runtimes in process, I made Foil, which was, again, kind of the same interface in terms of interop syntax, which worked over wire protocol, so that you now have two processes. One is the Common Lisp process, and the other is the JVM or the CLR. The problem there was, it didn't really do anything for I really don't want Common Lisp code or a Common Lisp deployment. You had these two things to deploy now. But this work definitely let me play around with some of the interoperability syntax, writing access to, say, Java stuff from Lisp. And a Clojure programmer would look at this is not Clojure, and recognize a lot of it. The calls to new, the constructor calls with dot, the dot calls for methods, the ability to define interfaces, in this case using this proxy, and implement interfaces and call methods. All those things were important and remain important, are things that Clojure can do. And the syntax was really being worked on already before I even decided to write a Lisp or do a functional Lisp. So the thing I eventually decided to do during my sabbatical was make a Lisp from scratch as opposed to modify or embed. Another set of sort of cross-cutting concerns, which had nothing to do with my experience with Common Lisp, but had more to do with some of the work I was doing in C# at the time, which was the election projection system, was a big, statistical specification for statistical models that had to run on election night. It was written in C#, and we decided to write it in a functional style, just sort of as a self-defense thing. And we did, and we ended up with a few things I thought were interesting. One was, it was very much not idiomatic code. Other developers that weren't part of our thinking about how to approach things functionally would look at it and just be bewildered by, for instance, having to track return values because they're used to methods that mutate things. And additionally, without any kind of persistent data structural library, we ended up using, the copy on write collection capabilities that were there, which are not a great fit and not great performance. So it really left me with functional programming is important. It definitely reduced the complexity of that system and made it more robust, but not being idiomatic and not having support for it made it hard to get people to follow. The other thing I decided to do was to host the language I was writing on the JVM or CLR. In other words, to have it be a language that emitted bytecode and ran on those runtimes. To me, hosting meant more than just the JVM or the CLR was an implementation detail, but that the JVM and the CLR were accessible, and that the language, Clojure in this case, would be accessible to it. In other words, it's not a layering thing; it's an embedding, if you will, and that the interop would be bidirectional. The other thing that had to be the case was it had to be fast enough to work where Java or C# would. Not necessarily as fast, but fast enough that I could sell it as a way to tackle problems that we would tackle in Java or C#. The last thing I wanted to do is to keep it simple and small. I mean, the big refreshing thing for me, as much as Common Lisp is a very large thing, most of its size has to do with a rich library. The language is small, not a small scheme, obviously. But the core of it, and going all the way back to McCarthy, it was sort of like, what's the minimum amount of stuff you need to bootstrap a language? And sort of following that, what's the minimum language you need to be an effective developer? And I thought it was a lot less than Java or C# and certainly less than C++. So keeping it small was an objective and remains an objective. So then it was a sort of an implementation project. What did I need that I didn't have? And the critical thing was I didn't have any high performance immutable data structures. We're talking about those hash tables and vectors. I wanted to be able to have some alternative for state management to locks and mutexes and that kind of thing. I wanted to have some sort of runtime polymorphism system. So what I'm talking about here specifically is the kinds of things that are yielded by Java interfaces, C++, virtual functions, the ability for a program to interact with new algorithms for the same interface at runtime, depending on the kind of data or the values of data that I was encountering. I wanted to fix that aspect of Lisp, of it being built on abstractions. I mean, certainly understandable given its history, but I wanted to redo that, try to put abstractions at the bottom, and of course the hosting. So to do the persistent hash maps, or to do the hash tables, I ended up eventually finding Bagwell's hash array map trees, and all I did was make which were not functional or immutable. What I did was just make a version of them that were persistent and immutable, and just use the sort of the ordinary path copying strategy. It ends up that Java's system array copy is quite efficient, and it made these competitively fast with Java util HashMap. Similarly, the same kind of 32-way branching tree structure was a viable way to do vectors that were, performed well enough to use. So this is a critical thing. If I wasn't able to pull this off, I don't think I would have continued during my sabbatical with Clojure. This was essential, I thought, to having something that was viable. For doing state, basically, I was looking at ML and SML at the time, and I saw they had the refs, and I liked that everything was immutable except this one thing, just a pointer-like thing. But there were, as far as I could see, no concurrency semantics around the refs. So the idea was just to add them In addition, I wanted to get away from sort of read, modify, write approach that you would take with variables, and instead use a commutation function. Say, there's something already there. Here's a function, apply it to what's already there, plus some arguments, and get the new value that will be there. So I I also took on writing an STM at the time, because that was the only thing that would sort of be competitive with the multi-update possibilities of mutexes and locks. And there's details in the paper. It's a MVCC approach that doesn't need read tracking. It ends up that this was super important for the storytelling of Clojure when I first did that. But in practice, I think the STM is used extremely rarely. There are a couple of other flavors of these refs in Clojure, in particular atoms that just use CAS. They don't support coordinated updates, but they are enough for most applications. Working on Lisp, the biggest thing was to sort of move away from the console, which was a concrete data type, to an abstraction over it, which I'll call seek or iSeek. Because you'll see later, I didn't actually end up with an answer to runtime polymorphism in time. I ended up implementing the abstractions using Java interfaces. And so there's an abstraction for consoles that support, first and rest and termination, but support an open set of implementations as opposed to being concrete. There were a bunch of just decisions you make when you want to write a Lisp. Is it a Lisp 1 or a Lisp 2? I liked Lisp 1 and schemes being a Lisp 1, but then you have the problems of how do you deal with macros, and Lisp 2 was sort of partially pointed at that problem. I ended up approaching that by using a non-interning reader, and this is probably a lot more Lisp specific than a non-Lisper would understand, so I'm not going to go into more of it now. The biggest thing, though, that I think is apparent to people who look at Clojure versus the other Lisps is that there are more things, and I think that they tend to presume that now there's syntax, and that you broke Lisp, which was always about being data structures, and I don't think that's the case. I think the way to think about Clojure's syntax is that the reader has been enhanced to support more data structures, but it's exactly the same strategy as before. The reader could read lists before. Now the reader can read lists and vectors and maps and sets. It ends up that vectors and maps and sets are used very rarely for language syntax. Vectors are used a little bit, but they're used quite a lot just to represent data literals. But it's still a read eval system, and it's still evaling code as data. There are a bunch of sophisticated aspects of both Scheme and Common Lisp that I just left out, like continuations and conditions, other things that I couldn't make happen that I would have liked to have, like tail call elimination. For hosting an interop, the strategy was to dynamically compile to bytecode. From there, the runtimes can get you to native code. So there's native bytecode and then native code, and things like hotspot will get you from bytecode to native code. So it's really great, and the JVM is a fantastic language target in that you just have to go that far, and then there's a bunch of quite mature infrastructure that can get you to high performance and inlining and things like that. There was a little syntactic sugar that's kind of non-Lisp in the dot operator. That's not first class the way almost everything else is. And then the sort of the big approach to hosting an interop, part of this being hosted, was to have sort of bidirectional conversion and copy-free compatibility. By that I mean, if you have a Java thing, a Java array list or Java hash table, and certain Clojure abstractions make sense for that, they just work. You don't need to copy your Java stuff into Clojure data structures. Similarly, if there are Java abstractions like iterability or being a collection, the Clojure implementations support those abstractions and those interfaces. So if somebody has written something in Java and it expects a collection to be passed, Clojure collections are Java collections, and they satisfy those interfaces, and they do not need to be copied or converted. And where possible, if the semantics match, I would try to use the Java thing directly. So strings were immutable in Java. That's good enough for Clojure, and so Clojure strings are Java strings. It was a common question, I think, of the reviewers and whatnot, sort of like, how did this work from a financing or funding standpoint? So I'll talk a little bit about that now. Like I said, I decided up front to take 2 years off, so I sort of had that framing and take some of my retirement savings to do that. And I did take that time to do the core design and the bulk of the implementation, including the data structure stuff I just talked about, and the syntax and hosting and bytecode generation, all in this time frame. I had originally intended to target both the CLR and the JVM, but I focused on the JVM for a bunch of reasons. One is I think it had stronger open source and library support, and the other is I thought it had better dynamic support than the CLR, which tended to be more focused on compiling up front. In the same time frame, I met and married my wife, who married me in spite of me having what seems to be objectively a terrible plan to make an unappealing language for no money, with no prospects of making money on it. And Steph has been a huge support throughout the entire time of development. And then by the fall of 2007, I was ready to go to the local Lisp meetup in New York City and present yet another Lisp. Having done that, for some reason, there was a reasonable amount of radiation of the existence of Clojure on, say, Hacker News and things like that. And I got a lot of interest and some early adopters, and I set up an IRC channel and a mailing list and sort of lived on that and saw people show up and ask questions, and had very high engagement with the early users of the language. When I initially released it, there was a very small core library, and so the next year or two were spent enhancing the core library, adding some language stuff, but primarily rounding out the library, making it make more sense, making things complete, improving the documentation. But people could show up on IRC and be like, I have your map and I can't do this with it. And in 15 minutes, I might push a new version of Clojure that gave them some new capability. My friend Eric Thorson, with whom I worked on the election system, also gave me some consulting work and bits through here, which helped supplement the retirement fund. But this was now 2 more years beyond what I anticipated. And so eventually by 2010, or the end of 2009, I knew this was going to come to a dead end from a funding standpoint. I had a funding drive with the community and had several companies and some individual users participate in funding ongoing development. That yielded partial income. I only did that for the 1 year because in the end, when you ask for funding, you end up getting more bosses than you want. And the number of bosses I wanted was 0. But it just kept going. The language grew, the number of users grew, the adoption by companies grew, and I just was fully engaged in building Clojure and enhancing it and supporting it. But critically, in 2010, Stu Holloway, who wrote the first book on Clojure, and Justin Getlin were running a consultancy and doing some Clojure work, but keen to do more. And I went down to meet with them to sort of figure out how we could work together, and pitched them the idea of Daytonic, which was a functional database concept I had been thinking about, and eventually partnered with them to build that. Stu worked with me in building it, and Justin ran the consulting company that supported it. In 2013, we merged the Daytonic effort with the broader consulting org, which was called Relevance. and we formed Cognitect, which was at this point now a consultancy that was substantially engaged in projects that involved Clojure and Daytonic. And doing this gave us revenue, and that allowed us to support the community more, allowed us to hire Alex Miller, who's a critical key contributor to Clojure, and also sort of the prime interface between the development effort and the community at large, and a sweet, very nice guy. And we're still going. So Cognitect ran sort of the sponsorship, if you will, of the Clojure development effort by keeping me alive. and Cognitect grew, and Daytonic grew to be a successful product. Eventually last year, Cognitect and Daytonic both became part of Nubank, which was a big consumer of Daytonic. And I'll talk a little bit more about that later. And that's been great also. That's more staff now working on both Clojure and Daytonic. In addition, at Nubank, we were able to directly fund some community members who are working on libraries and training and things that we think are useful to the community. Speaking of the community is great. Again, there's a lot in the paper about the community and sort of historical details, but it's obviously one person can't support everyone, and the community has been great at supporting new users. They've written books, they've given conference talks, and built libraries, which is important. Being a Lisp, it's a small language, and most of the growth should come in libraries, not in language enhancements. In addition, we've accepted bug reports and patches from the community, but Clojure never really became sort of a collaborative community development effort. I personally didn't anticipate even people expecting that in open sourcing it, and it was probably my naivete around how open source had been working and what people's expectations are of open source, meaning open and collaborative development. And I would say Clojure is somewhat atypical for open source in being open but not collaborative. And I think there are some advantages to that, both personally and in the result. But one community thing I want to call out is during the course of Clojure, I started an endeavor in 2011 to make a version of Clojure that could run on the JavaScript runtime, and particularly in browsers. And I built the initial version of ClojureScript in 2011, but eventually David Nolan took over the stewardship of that. And as you'll see later, I think followed along with the stewardship model of Clojure itself, and has done a terrific job. And ClojureScript is much more of a community effort and not something that I've driven other than launching it. So that's a big community success story. Just so you understand a little bit about what kind of people come to Clojure and use Clojure, it's not Lispers. It's not people who used Common Lisp or Scheme before. It's overwhelmingly, as you see here, object-oriented programmers who adopt Clojure. Java is the #1 place people come from, but you also see Python, JavaScript, and Ruby, and C and C++, which makes sense to me. Another characteristic of Clojure programmers is they trend more towards the experience side, but by no means is this uniform. So this diagram plots years of programming experience and salary for a bunch of programming languages, and you see Clojure way over to the right in years of experience, although this graph starts at 7.5 years, so it's not like linear, back all the way to 0 years. Up there with F# and Erlang, so we're a bunch of languages for experienced developers who are tired of it and are looking for something a little bit more rigorous, being functional. There's a bunch of stuff in the timeline here, things that, features. You can just see that there's been a regular release cadence. The feature development is front-weighted, but people have written books. I have not written a book on Clojure, but many people have. Libraries arose around, especially initially, web programming, but also logic programming and database programming and things like that. In addition, I'll talk later about talks, but some of the big motivational and influential talks that I gave were done in this time period. Moving forward, again, more releases, some more features, a bunch more in the tooling space, and a regular set of Clojure Community events and conferences. So there's now several conferences held every year at different places with different sponsors around Clojure. And at the time I started writing the paper for Hopple, which is now a couple of years ago, there were already 32,000 Clojure GitHub repositories and 20 books, and there were Clojure modes for all the editors and things like that. Here are some of the books, and you can see that they range from books about sort of the ideas behind Clojure to just how to get things done to how to do very particular things like machine learning or high performance computing or web or things like that. A bunch of tools have been built. This is one example, which is Clojure environment for IntelliJ, which is popular Java editing environment. And the reason why I like showing it is because it shows what it would, to a Java programmer, be a very recognizable development experience with structure, navigation, and project management, syntax highlighting, code completion, and embedded documentation and things like that. None of that is precluded by Clojure being a Lisp or Clojure being dynamic. So this is the kind of thing that the community has built in terms of tooling. That doesn't count at all some of the tooling we get for free by merely being implemented on the JVM, like debuggers or profilers and things like that, that just were written for Java but work with Clojure by virtue of the fact that it emits bytecode. To sort of editorialize a little bit in retrospect, I think things, I'm presuming a lot of the audience here are language designers looking to get their languages adopted. And so if you want to try this at home, some of the things I think matter to Clojure are being very accessible. So like I said, I was living on the IRC. If you read the logs back from when I first released Clojure, sort of any time of day I was on there. I was fascinated that anyone was using it. So it was interesting to me to see people show up and ask questions, but I did, and it was addicting to be there, and quite thrilling, the early days of Clojure on the IRC. Also the mailing list. I think having a unique name for Clojure is important. I strongly recommend you come up with a unique name for your language so that the search is good. If you overlap with an ordinary word, it's just going to be harder to find your stuff. My brother made a great logo. I'm sure that mattered. I gave a lot of talks. I gave talks at developer conferences. This is for professional developers, mostly not about Clojure. Primarily those talks were about the ideas behind functional programming and were very general. But I also, trotted out to a bunch of user groups, the Java user group in New York City, and also some hardcore Lispers at MIT to give talks about Clojure, Clojure for Java programmers, Clojure for Lisp programmers. And all these talks eventually ended up on YouTube. And I think that is huge. Having talks aimed at specific audiences about topics that matter on YouTube is important. Clojure being hosted made it easy for people to sneak it in. It wasn't like, we're going to adopt Clojure today. A typical Java application is using hundreds of libraries, and if Clojure is one of them, I don't know how anybody really knows. And it absolutely has gotten adopted via the back door that way. I do think that the problems I enumerated earlier were real, and that people share those problems. They don't often share the realization that they have those problems. And I often hear, after someone has adopted Clojure, I didn't realize how much stress I was suffering from writing code in an imperative way. But they are real problems of programming. I think that Clojure isn't a gentle intro to functional programming because it really only takes on idiomatic immutability and programming with pure functions and those data structures and data literals. It doesn't, force you to also take on sort of a bigger a bigger thing in an elaborate type system. And as far as ClojureScript, the ability to run the same language in the browser is quite big for that. There are lots of Clojure shops that write both the front end and the back end of the code in Clojure. And ClojureScript, quite importantly, is Clojure. It's not a subset. It's not a dialect. It's pretty much fully Clojure. I think Clojure, in the end, solves some problems that this is definitely Monday morning, retrospective quarterbacking. I didn't set out to solve, but I think it ended up being suitable for solving. One is, how do you do information programming? I don't really have time now to talk much about that, but I think that there's a big difference between programming the mechanics of a program, the data structures, a compiler, and algorithms, and what kinds of constructs are useful for representing mechanisms versus what kinds of constructs are useful for representing information, the stuff we happen to know about this customer, the stuff I need to know about this customer in this context. That's really, that kind of programming dominates application code. I talked a little bit about creeping concretion with classes before. Not having any classes means you don't have that problem. Similarly, I think that when you have a object-oriented class-based ecosystem, the framework that comes with the language is dominant, and it's hard to get traction on third-party interfaces and frameworks. Because everything in Clojure is data in, data out, it's easy to decide how to approach the interface to your library. And it's easy to have independently written library things that work together. I think that, to the extent that systems are now largely composed of services, independent processes that interact over wires using, transporting fundamentally shared understandings of data structures across those wires, working in a language that does the same thing all the time, works with fundamental shared basic data structures all day long, means there's a lot less impedance when you want to participate in a service-based architecture. You don't have parochial views of how data is represented. You have quite common views of how data is represented, and you're ready to go on and off a wire. I think that's big. The other thing that Clojure avoided substantially was instabilities for people who are using Clojure in production, because it wasn't ever intended to be a place for experimentation, and the stewardship over time has very much eschewed experimentation in the language. You can see that in this diagram. This is a code retention diagram, so it shows when code has been introduced, colored by year, and then what happened to that code over time. So if the code got changed or removed, you would see that band would diminish across time. And you can see, I think, what I would call a nice layer cake in Clojure, in that there's a high degree of stability. We definitely tend to avoid changing things except to integrate fixes, but we don't change things just to change them, or because we think we have a very slightly better way to do it, in an effort to maximize the stability for people who are consuming it. And that is overwhelmingly part of what people would report in using Clojure, is their very old code works perfectly well, and they're happy to update to a new version of Clojure because they know we're not going to mess with them. And it's a credit to David Nolan that they've run the ClojureScript ship in a very similar way, layer cake. So I'm going to end with an anecdote, which is neither small nor short temporally. So I think it may not be indicative of everyone, but it shows what's possible. A Nubank was a startup in 2013 looking to build a digital bank and change banking in Brazil and elsewhere. And so it started from scratch in 2013 through today, where now there are 800 engineers, most of whom had no prior functional programming or Clojure experience. That's important because I think people are reluctant to adopt Clojure or functional programming because it's different or whatnot. But this proves you can certainly train people, get them up to speed, and have them become productive. The overall system involves 577 Clojure services and 165 Lambdas. There are about 3.9 million lines of Clojure at Nubank. That is an unbelievable amount of Clojure because Clojure is pretty concise. Although if you divide it by the number of services, you'll see that the size of each service is actually competitively small with developing services in other languages. There are 320 Daytonic databases. So Nubank was a Daytonic customer, is a Daytonic user, and a big one. So you're talking about applications written in Clojure running on a database written in Clojure. There are about 1,000 deploys done per week, 60 billion HTTP requests handled, and 30 billion Kafka messages consumed. And this has yielded a significant business, as represented by the final two facts here. So I think Clojure, does what I intended. It's something you can use to build production programs, and I couldn't be happier to see it used today by so many people. And thank you very much for attending this, and I'll see you at the QA.
Okay, thank you, Rich, for an interesting talk, and we have some questions queued up already. So let's dig right into them. I'm going to start with a question from Brian Harvey. Could you say more about the open but not collaborative development? To what extent do you accept or solicit pull requests from others? I ask because Snap is facing exactly this issue. Jens wants to do it all himself, but people are clamoring for things he doesn't have time to do.
So actually, we don't accept pull requests at all because pull requests are not values. We do accept patches, but not really in the area where people are looking to invent or enhance. Primarily, we only look for bug fixes or documentation fixes and things like that. So it is open in that sense. There is a place to report problems and/or submit patches with problems, but it's not open in that there's no place to sort of say, I'd like Clojure to have this feature and add the feature. I don't want my own feature enhancements, nor others. I think the effort to keep Clojure small means I'd like to see the emphasis on libraries. And so most community input is via libraries.
Okay, a question from Paul Pfister. What are the features that you've deliberately chosen not to add to Clojure, feature-wise and not back compatibility-wise, but that you believe would be nice in another general-purpose Lisp? For example, features like first-class environments, first-class FexSpur, first-class continuations. So I guess the question is, if you wouldn't put it in Clojure, but you think it would be nice in another Lisp, what's your wish list?
So I think to the extent it's an exercise in less is more and smaller languages or more, I think most of the things that were listed there, you'd really have to make an argument for why they pay for themselves from a complexity to benefit standpoint. I mean, it's hard to talk that way about continuations to a schemer, but the only thing I really missed, and it was something I would have liked actually, but I couldn't make work, would be tail calls. That's certainly something I think all languages should have.
I'll follow up with that. If the JVM supported tail calls, would it be easier to put them into Clojure?
Oh yeah, if the JVM had tail calls, Clojure would have tail calls. Well, if they had it when I started Clojure, that would definitely be the case.
Understood. Okay, a question from Theodore. How has the kind of problems Clojure is meant to solve changed from 1.0 to 1.11? And then there's another follow-up question, but let's just start with that.
I don't think that the kinds of problems have changed. I don't think that Clojure has had sort of any kind of special purpose facilities from the beginning, and it's been general purpose, so it's used widely across medical applications and finance applications and web apps and data analysis. So in that respect, I don't think that the problems it's looking to solve have changed, and it certainly hasn't taken on something, specific to the current trends like differentiability or something like that.
Okay, and the follow-up is a comment followed by a question. Clojure has long been a good choice for long-running processes. Though a REPL workflow has advantages in other domains, interactive programming is important in data science and scientific programming. A tangible runtime makes it easier to benchmark high-performance code. Data visualization from a REPL is interactive. Are these happy side effects or design targets?
I mean, I think they're design targets of Lisp before Clojure, and Clojure is just, agreeing. I think interactive programming is critically important, and being able to try your ideas and see what's happening, to have your context loaded while you're developing code and not have a sort of compile run cycle. It just changes the way you think about programming. And certainly agree about the data science applications as well. I think it still remains a growth area for Clojure to sort of seek out some of the facilities that were common in Lisps and Smalltalks, from their heyday. We don't have rich environments like that yet, and I think that it's fine to sort of meet people at the interactive environments they're used to, and IntelliJ and things like that. But it's nowhere near as good as the heyday of Lisp and Smalltalk. I think there's a lot more tool work that could be done to bring us back to where we were.
Will Crichton of Stanford asks, many dynamically typed languages like Python and JavaScript have been moving to add type systems to manage complexity in large code bases. Is typed Clojure the future, or do you think there are aspects of dynamism that are helpful for reducing complexity that aren't accessible with static typing?
This is always going to be the big question. So I don't think that they're going to achieve what they intend with that. I don't think the types, especially as applied to something like TypeScript or Java or C++, are rich enough for solving significant problems, especially if your program is still going to be imperative. Your problems will be dominated by state and not by the things those kinds of type systems can help. I do think that there are costs, and I sort of hinted at it when I talked about this creeping concretion. When people apply types to information and end up with classes for customer and whatnot, they end up with far more specific code than they ought to, and they end up with far less reusability of their algorithms and their libraries. And so I think it's not just about dynamism. I think it has to do with, are you programming to data structures with a generic notion of accessors, say, for instance, for associative data structures, or are you trying to do information programming with objects or types, and therefore sort of a full enumeration? And I think full enumeration of, a customer has X and Y and Z yields brittle programs that are hard to extend, that have a lot of specificity, are many times larger and far less general and flexible. So it's a cost benefit thing, and I think that there are some benefits obviously to types, but the costs are under-examined.
All right, I have a question for you. One of your slides referred to Clojure as providing a gentle introduction to functional programming, and it listed as examples idiomatic immutability and pure functions. I'm interested in what you would consider not so gentle aspects of functional programming. For example, is it higher order functions like map and reduce, or is it something else that's less gentle?
So today I think people have more familiarity with map and filter and whatnot, because it's been common in, well, MapReduce became an algorithmic exercise for data processing outside of programming languages, and also it's more common in other languages. No, the biggest hurdle is still immutability, not having loops that update in place, even local counters in place, capturing return values and as values is still the hurdle. And as gentle as Clojure could be, it's not something I think there's a syntactic solution for. If people have been developing in an imperative style for a long period of time, there's just going to be a hurdle to having that taken away and just saying, what do you do instead?
Okay, and a related question from Connor Hoekstra of NVIDIA. Clojure is one of the only languages to have symmetry in the naming of their reduce and scan algorithms, reduce and reductions in Clojure. Is there a story behind the naming here, or how that came to be?
Well, so we have a thing in the Clojure community, a meme, especially from the early days, about playing the naming game. And I think we definitely, I love naming things. I think it's one of the biggest challenges, and we work really hard at trying to do that well. In terms of reduce and reductions, yeah, and there are a number of things like that. Certainly when we got involved in the transducers, that sort of forced you to sort of lift out one more level as you take the source data structure out. You end up needing to name that other thing. But I don't think symmetry is sort of its own target for Clojure. It's just sort of being careful about names.
Okay, here's a question from Richard Gabriel. I have some information pipelines to Brazil, and I hear a lot about Daytonic and not as much about Clojure, unless I mention the connection. Can you comment on how Daytonic has interacted with or driven Clojure adoption, at least in Brazil and perhaps elsewhere?
Yeah, I don't think I could talk about Brazil specifically, but it's certainly been the case that we have had people adopt Clojure because they adopted Daytonic first. So a lot of financial institutions, they like the idea of Daytonic. It has great auditability and tangible transactions, and sort of how your database got to be the state it's in, and you've lost nothing because it's append only or sort of accrete only. Of course, they get there and they see the principles that underlie Clojure are present there, and there's absolutely minimal friction in consuming Daytonic from Clojure. So yeah, I think that many people adopted Clojure because they adopted Daytonic, but not the majority of Clojure users. A significant portion of Daytonic users chose the database first and the language second.
Okay, in a previous answer, you referred briefly to transducers, and I think that's actually a fairly central concept in the design of Clojure. Could you talk a little bit more about that and how that idea grew and how it's used?
Well, I mean, I wish I had thought of it early. It was a late idea, but it was born of looking at the challenges of Clojure has a laziness construct, and when you see laziness anywhere in Haskell or whatnot, you end up with this whole how do you eliminate the overheads associated with composing streams? And there are a lot of different ideas around that. I had worked on reducers at one point to try to get more parallelism in play, but there's still sort of the raw overheads that, for instance, facilities like Stream Fusion target were present in Clojure, and so transducers were an effort to sort of solve that problem in Clojure. Having sort of developed that, were I to go back, that would be a foundational concept in Clojure. I didn't think of it back when I started Clojure, but were I to rewrite Clojure, transducers would be at or near the bottom of any kind of processing methodology, because I think it's sort of a pure way to talk about algorithmic composition sort of independent of the source. And it both works with pull and push sources and with data streams and event streams in ways that people have had to do parallel systems before.
Okay, so speaking of parallelism, I'm curious to know to what extent the concurrency features, so for example, you mentioned the refs and supporting either compare and swap or a read, modify, write kind of thing, or in your case, commutation functions that would just sort of provide a transformation on the value in place. I'm curious to know to what extent those features are used by end application programmers, or to what extent their uses are mostly buried in support libraries, which are then used.
I think they're mostly used by end user programmers and rarely by libraries, because that aspect of a program is usually at the edge. So if you're going to have an algorithmic library that does something interesting, it's going to be almost 100% functional. And then, if that stuff's going to have to go over a wire or be the state of a program, it's the application programmer who's going to choose to put a reference to that state in an atom. So they end up being edge and therefore end user concerns, and rarely in libraries. if it wasn't a library, that library would essentially be stateful and have kinds of, objections to its use, because you'd have to understand how the inside of it worked in a way that a functional library doesn't. So I don't see it much in libraries at all. It's left to the user to deal with the edges of their program.
I suppose the question I was really asking is whether libraries of additional communications or parallelism abstractions get built out of the lower level ones. And it sounds like the ones that are already provided are doing the job.
Yeah, I mean, like I said, even the STM rarely gets used. An atom holding a pointer to associative, persistent map is the 95% case, I think, for applications. And we've written large applications. Daytonic itself is an entire database, and it has one atom around the database. That's it, and it uses some queues and whatnot for data flow. But you end up needing very little.
Okay, a question again from Will Crichton of Stanford. I've noticed that you use a number of terms like concretion and complect to talk about specific aspects of complexity in software design. How did you decide on these terms? Do you feel there's a missing science of complexity management that we should be exploring with these kinds of concepts?
So, complect came from a talk. Again, I love the dictionary, and it means something very specific in braiding. And what I was trying to do is give more specificity to an old notion, which is coupling. And I think that people who write systems understand coupling sort of intuitively. But if we want to sort of address problems in larger systems that involve extensive coupling, I think we have to have more specific terms that identify or call out what exactly, where does coupling come from? And so complecting is a word that is very specific about a kind of coupling. The concretion thing, I think, is, again, it's something I've started to use, and it's a hard concept to get across to people when they, because I don't think, it's like many things, you don't understand you have the problem while you're having it necessarily. And so if you have a program and you have hundreds of classes that are each specific to a particular kind of information, each class, again, I'm talking about ordinary object-oriented programming, each class defines its own language. And we've looked at Java classes, for instance, for doing HTTP. And one typical Java class will have inside one class, 4 independent implementations of what you would call an associative map with different names. Everything about that is bespoke, and all the code that consumes or interacts with that class is also bespoke. And so that code is concrete in such a way as to be specific, and also concrete in such a way as to be inflexible. In other words, it can't be applied to some other class. And if one side changes, the other side has to change, or they'll break. So I literally mean concrete in that sort of rigidity. But yes, I don't know. I think there are so many conversations we should be having that we're not, about how to make software more flexible, and also about programming over time.
All right, a question again from Connor Hoekstra of NVIDIA. The thrush operators, aka thread first, thread last macros, and how they play with algorithms in Clojure core leads to some extremely beautiful and elegant code. Can you shed light on what went into the designing the algorithms so that they work so well with the thrush operators?
So there's 2 aspects to those operators. One is it was always an argument amongst Lisp programmers that, like, of course you should know how to build things, from the right side back out and have all these nested parens and a pile of closing right parens. But I actually don't agree. I think that that's something that needed to be fixed. So there's just sort of the sugar of it. Specifically, though, there are the 2 flavors of the thrush operator, one with a single arrow, one with a double, or saying a single greater than sign, and one with a double. And that is an interesting difference. And in there, I think that there are 2 flavors of accessors. And this was something I had to explain to people a lot early on. One are more object-oriented, so you have a property of a thing, in which case the thing will be the first argument of the function. So to this thing, do some stuff. And that's the single arrow operator. The other is when you do processes like mapping and filtering that involve streams, you often the data you have up front is not the target, but the parameters. So I know I want to filter this stream with this function, or I want to map this function across the stream. In which case, the last thing you want to supply, or sort of the thing you want to bind last, is the collection. And that yields the two flavors of thrush operator. And really, all you have to do is correctly assign your function to one of those two categories. And then the thrush operator seems to be incredibly elegant. But it's really not. There's only two ideas, and I have both of them there. And if you pick correctly, it will look good.
Okay, I'll ask you one last question. Is there anything else you want us to take away about the design of Clojure, about your experience in building it and building user community?
I think the biggest thing is just that Clojure is really small and simple, and it's adequate. And I think we don't, we're so ambitious in the kinds of things we take on in programming language design that we don't value enough that sort of minimality. And programmers are engaged in very, very complex domains now, and we should be out of their way. Our tools should be out of their way, not complex things in and of themselves. But if it's not required, I think it should be taken out, and we should try to allow programmers to solve problems with smaller solutions, because I think that you can. And something like Nubank being built out of Clojure, I think is evidence of that. That's a giant system.
Okay, thank you, Rich. I will conclude by echoing a last comment from Theodore Hegeland. I just want to add a thank you for keeping Clojure simple.
Well, you're welcome, and thanks very much for having me be part of Hopple. It's been a pleasure.
Thank you so much for Q&A. Okay, thank you. That ends this session.